Is my screen visible to all of you?
Yes, it's visible, sir.
Okay, fine, thank you. So today we will see about this LSTMs, long short-term memory. Uh, we'll give a brief introduction what we have dealt earlier about this feed-forward neural networks and then RNNs. Then we'll enter into the LSTMs. So we know that like in feed-forward neural network, the output at time t is independent of the time t minus 1, the output at t minus 1. So right, this is the input that you are giving it, and then you pass through the hidden layers and you get the attain the output. So here this output is independent. Suppose this is the inputs that is given is maybe like at a t minus 1, and at the time t the output would be independent of the output of t minus 1. So there is no dependency between two outputs, right? So we've entered into learning the concept of recurrent neural networks. So this, we said that these are networks with feedback loops which has got the recurrent edges. Okay, this is what we have seen. The recurrent edges also we had it, and the output at current time step depends on the current input as well as the previous state, right? Via the current edges. This is what we have seen it. So this is the input and this is the output, and we have the recurrent edges here. And if you unfold this one with respect to time, you can see that at t minus t equal to 1, so this is the output that you are going to get it. This is the inputs, and then this is the output that you are going to get at time t minus t equal to 2. Okay, t equal to 1 and this is t equal to 2. What you have seen it, you have taken borrowed or taken the input along with this input at t equal to 2. You have taken the processed activity of this t equal to 1, or maybe the output of t equal to 1 also you have taken into consideration. Okay, so that's why you can say that this is recurrent neural networks. So when you unfold this one, this particular neural network, okay, this particular neural network, what is given here, you can get it with respect to time. You can get it this way. This is what we have seen yesterday, and also we have seen like how a training in neural network is being done. We use like a regular backpropagation applied to RNN with respect to unfolded time, uh, and we can also use it this truncated backpropagation through time. Okay, this one also can be used where we say that like the backpropagation is done at some time periods or time intervals. That also we have seen, and we also yesterday saw like how the backpropagation takes place. Right now, uh, the problem here is that uh, it can't capture long-term dependencies due to vanishing or exploding gradients during the backpropagation, right? So what is the basic formula for a RNN? It is given here. H of t, this output, okay, here H of t, this is depend on the C of t at C, the value of C at time t, and its weight multiplied by its weight. Okay, passed through a sigmoid function here. Okay, pass through some squashing function. So here WC weight into this C of t. And how do you get this C of t? Basically C of t is measured as this input into this weight, input at time into this weight, along with this one the previous input. Okay, or the previous values here, the previous WR. Okay, previous red value or previous value, you are going to take it into this time, the into the input x of t. So this is how you are going to get it, the output for a neural network. Now with respect to, suppose you wanted to get the output at position 3. So this is 0 1 2 3 for example. Okay, now what happens is h of 3, that is h of 3 at 0, 1, 2, 3. Okay, this same thing we are unfolding it with respect to time and time stamps. So h of t equal to, what you are going to get it here, WC into C of 3. WC is nothing but here, what you are trying to take it, the weight. Okay, the weight into C of 3. C of 3 here, this is C of 3, this is C of 0, C of 1, C of 2, C of 3, for example. Okay, so C of 3 you are trying to take it. So this C of 3 can be again expanded. Okay, C of 3 can be expanded again. You use C of 3 is nothing but, what you are going to do it, Wx into x of 3 input at time 3 plus Wr, the value which is attained from the previous output, into C of 2. Okay, C of 2, C of 2, the earlier value. From here you are going to get it from this one with some weight plus this input with some weight. That is what you are supposed to get it, right? So this is C of 3, means you need to get it. This C of 3 is this plus this, right? This you are supposed to get it. Now this, all these things pass through a squashing function sigmoid. Again, this C of 2 can be expanded again with respect to Wx, the function Wx into x of 2 plus Wr into C of 1 passed through some squashing function. This again, C of 1 can be expanded like this. Of course, this value will be 0 because the initial value will not be available here. And when you pass like this through different squashing functions, you are going to get this particular value h of 3. The output here, you are going to get it. You need to remember that how, with respect to different sigmoid functions applied on the data, how the graph varies. Okay, if it is a single sigmoid function, it goes on like this. Definitely single the sigmoid function is 0 to 1. Okay, and again something you get it, maybe like the graph varies like this if it is double sigmoids, triple sigmoids, and if it is like quadruple sigmoids, how it varies, how the graph varies, just it is given here for your understanding, easy understanding of this RNNs. Okay, now so we have the problem of long-term dependencies. So a type of RNN, that's why in order to achieve these long-term dependencies, we use this memory networks or long short-term memory networks. As I said you yesterday, I had been giving you one example of stating like suppose there is a sentence like, I lived in Odisha for 10 years and I was very happy with the people over there and we used to always chit chat and something like that I had given, and at last I gave you a sentence called, I can speak dash. So you named it that it is Odia, right? So it means that there is a dependency. There is a dependency, right? There is a dependency of the some term which was stated earlier, or maybe like suppose I am writing a review about a camera. Okay, about a camera, or maybe like about a mobile phone. Just I am writing a review. So I write so many things. I purchased a Samsung camera, a Samsung mobile, maybe, or I purchased a iPhone 12. Then I give descriptions about that one. Next, the camera was fabulous. The picture quality is very good. Then there is a complete noise cancellation. Many things I give it. Though I am not complete, I have not complete. So I give it maybe like some 1,000 words. I write it the review. Then at last I say that though I have not explored the complete features of iPhone, still I recommend to purchase dash. बोल के दे दूंगा. So if I give it like that, then definitely it means that after 1,000 words also it is referring to that particular, the first term which we used as iPhone 12. This is, so there should be some dependency between some sentences or maybe some words. There are some dependencies, but conventional RNN do not hold these dependencies. It is because it lacks memory. It only passes through some a squashing function, only one squashing function, and ultimately it attains the result. Whereas now we will enter into a new concept that is long short-term memory networks, which is a type of RNN architecture that addresses the vanishing or exploding gradient problem and allows learning of long-term dependencies. So why we cannot do it in RNN? The concept is that because we are having this vanishing or exploding gradients. So how we can overcome this? So in order to overcome this one only, we need to go with some long-term memories. Okay. So recent Ryzen in this LSTMs with state of art performance has given, like in the area of speech recognition, language modeling, translation, image captioning. So any sequence leveling or sequence analysis applications, this LSTM is being heavily used. This has been heavily used. Okay. Of course, there are advances which came after this LSTMs also, where we are going to see few things also. So now if you see, we are mostly concerned about these memory networks. Okay, long or short term memories. So this long or short term memory basically comprises of these few parts. You have a memory cell. Okay, you have a memory cell. This memory cell is supported by the forget gate, which is again self-recurrent connection, which has the self-recurrent connection, and you have the input gate and you have the output gate. Okay, this is like this memory cell, this completely combining of this forget gate, input gate and output gate. This we call it as a memory cell combinedly. It means that this memory cell basically is a like a complete line like this, which like there is a forget gate stating like what things need to be forgotten, and there is a input gate or new input, whatever you are giving it, like whether new input need to be added or whether it should be discarded, like that it is given. And then the output gate. Okay, what things need to be continued forward. Okay, to the next input. So this is the memory cell, you can say that. So the central idea of here is that you should have a memory cell which can maintain its state over time. Okay, which can, it should be able to maintain its state over the time. And now this this if you say like it should be able to consist of an explicit memory. Here explicit memory means what we try to do it, we simply try to get it like we have a cell vector. Okay, a vector, we have to get a cell vector and some gating units which regulates the information flow into and from out of the memory. So this is completely as explained. This is the LSTM memory cell. Okay, now the LSTM memory cell, it is given here completely. You can see this like uh, in this LSTM memory cell, you can see here, this is the memory cell basically. Okay, this is the cell as I show you earlier. This is the cell. Okay, this is the memory cell supported by this part is the forget gate. Okay, this part is the forget gate. This part is the input gate, and this part is the output gate. Okay, this part is the output gate. Now you see here, please concentrate on this particular slide, which is very much important. And this is you can say that what are the inputs that you are giving to this memory cell. Basically the input is the input vector, basically xt here. Okay, this one, and it gives input to different gates also, maybe like the forget cell, forget gate, then the input gate and the output gate also, it gives the input. This xt can be taken, and then memory from previous block. This is c t minus 1 at current time t. You are using the memory value of c t minus 1. Okay, this value also you are going to give the input, then the output of previous block. So the output t minus 1 t, this is h t minus 1, you are taking the output. This is the output. Okay, you are taking from the previous, and also you are giving feeding as an input to different gates over here. Outputs, what do you get? The output of this memory cell, ct and ht, right? CT is nothing but the memory from the current block. What is the memory values? What should be carry forward from this memory values, and what is the output of the current block? This is the output of the current block. Okay, either you can display it there or you can make it forward and then pass it to the next cell. It depends upon what type of RNN that you are using, whether it is many to one or one to many, or maybe like many to many or like that. Okay, we see. So what type of, whether we give the output here only or we pass it that one to the next one. Okay, fine. So we use two squashing functions here or activation functions here. One is the sigmoid layer here, sigmoid layer, which you know that like activation functions you must have seen, like tan h is there, which is ranging from -1 to +1. The values range from -1 to +1, and you have got sigmoid layer from 0 to 1, and also you have got ReLU layer from either 0 or 1, right? These type of things. But here you are going to use it for different activities, different gates you are going to use it. So we use here the activation functions for in order to cut these non-linearities. So we have this, we use two activation functions here. One is the sigmoid layer and another one is the tanh layer. Okay, hyperbolic tangent layer. These two things that we use it, and also uh, we give this B is the bias. Okay, this is the bias that we give it some values. Okay, this we give it here, and various operations that get performed in the memory cell are element wise multiplication, vector multiplication basically, or it may be like a element wise summation or concatenation. These are the various operations that happen in this memory cell. Okay, so you give here, see something like this. It is one figure on the right side, it is given here. This is a gate. So when we tell a gate with a sigmoid layer followed by a point-wise multiplication. See, if it is this represents a gate with sigmoid layer. So the data is passed through the sigmoid layer, and then some multiplication activities, point-wise multiplication activity is being done. Suppose pass it and then plus symbol is there. It means that element-wise summation or concatenation activity is being done. So this is the simplified schematic diagram of the for the reference it is given here. Now let us try to see about each of these gates. Okay, one by one let us try to see about this gate. First one is about the cell state vector. So this part is the cell state vector. Okay, this part is the, basically this is, you can say that this is the cell state, this complete line that is going. Okay, this is the cell state. Okay, this represent what is the state of the vector. It means that what things need to be forgotten, what data which one need to be forgotten and which one need to be carried forward. Okay, when the new information comes, uh, suppose I am speaking about a person. Okay, for example, Ram and Syam were very good friends. Ram was a very good boy. Then I am trying to speak something about Ram like that, and Syam is very intelligent boy. Then he used to always score first. So what do I mean by he here, whether it is Ram or Syam? So earlier when I used to tell Ram, it refers to Ram. Whereas next time after stating some sentences about Syam, and then trying to give about he, here, whom does this pronoun mean to? He, it means to Syam. Okay. So I hope you are getting me. So in that case, the he value, it means that representing he for Ram should be avoided, whereas representing he for Sham has to be taken. It means that forgotten, that value need to be forgotten. So Ram has to be forgotten and Sham has to be the new information. Sham here. Okay, he means Sham here. Okay, so this need to be carried forward. So all these details are available in the cell state vector. In this vector, so so some forgotten activity, what needs to be forgotten, or simply if it is not to be forgotten, then it is carried forward like that. Okay, maybe like the based on the current new information also, whether it is to be forgotten or it need to be carried forward. This represents the cell state vector or the memory cell basically. Okay, this represents the memory because this is supported by different gates here. Okay, so it undergoes changes via forgetting of the old memory using the forget gate and addition of new information using some input gate. Okay, I hope you are getting me. I am clear, right? So this is, so I please remember that this is the cell state vector. Okay, this is the cell state vector basically. Now what need to be given and what need to be carry forwarded. Okay, what need to be remembered and what need to be carry forward. So you can say that this is the first step here. Okay, this step, it means to say that like this cell state vector has to be taken into consideration for the complete working of the RNN, supported by this forget gate, then this input gate, then like concatenating it here with different things. Okay, or maybe like multiplying, you are trying to take the storing the vector value here, then about the output. So four states we will try to see it. So we use various gates here. Okay, we use various gates, and this gate is sigmoid neural net layer followed by a pointwise multiplication operator. This is what is a gate. And then like gates control the flow of information to and from the memory, and gates are controlled by a concatenation of the output from the previous time step, and then the current input and the optionally some cell state vector also are taken into consideration. So we'll see about the first gate, that is the forget gate. This basically controls the information to throw away from memory. So this is the first step of LSTM to identify those information that are not required and will be thrown away from the cell state. So this decision is basically made by sigmoid layer called as the forget layer, right? This sigmoid layer is used here. If you see here, what would be the operation, mathematical operation, what mathematical operation is taken here? This so WF, this one is the weight. Okay, this weight, you can say that, and H t minus 1, this is the output. Okay, this is the output t minus 1, earlier this one, earlier output. Then the input xt here is the new input that you are going to give it, and some bias b0. Okay, bf, this is the bias at 0, or like a bf. Okay, now here, so these things, these three inputs are given. Okay, you are making this, you are providing ht minus 1, the previous output, and the current input, you are multiplying with respect to the weights wf. Okay, for the forget gate weight, plus the bias, forget gate bias, you are giving it, and this one you are passing through, you are passing through a squashing function or the activation function sigmoid layer. This you are going to get the ft. So this value is ft. This is the first step that you are performing for a LSTM. Okay, so this here, please, ft, this ft value is here, this is ft. Okay, this is PDF, I'm not able to write it, so I'm not writing it, but this is this particular line here, this is the output of this squashing function is ft. Okay, please remember this. Now you try to go with the second layer. What is that second layer? You see here the input gate. The second layer is the input gate. What is this? What does this input gate basically do? This step here is to decide what new information we are going to store in the cell state. Okay, what new information we are supposed to store in the cell state. So this whole process comprises of the steps like what you are trying to do it here. A sigmoid layer called the input gate layer decides which value to be updated next. Okay, here, and also you are using a tanh layer, hyperbolic tangent layer, to create a vector of new candidate values that could be added to the state. So here, then in that case, what are the things that you are trying to perform here? This and this. So here you see IT. So this value is IT. IT you are passing. So the value of the H t minus 1. Okay, output of the previous state. Okay, output of the previous state, and XT, the current input also. You are multiplying with the input weight. Okay, WI, input weight, plus you are adding the bias. Okay, this is this one. Okay, VI input bias, you are trying to make it and pass it through the sigmoid function, and you are going to get the IT. Okay, the input at time t. Along with this one, so CT bar, what you are trying to take it, this one, how you are getting this CT bar, this particular output after tan H, this is the CT bar. Okay, now here, what are the things that you are giving here? The previous output of HT. Okay, then you are trying to give the value from XT. Okay, XT, the current input, and HT passed through some weighting function. Okay, current weighting function here, then plus the BC bias. This 2 represents the bias here. Okay, this 2 represents the bias here. So this passed through a tan H activation function. When this passed through a tan H activation function, this CT value you are going to get it. Okay, this CT bar you are going to get. So here this is IT, this is FT, this is IT, and this is CT. Okay, now at the third step, okay, at the third step, what you are supposed to do it. Let us see this. You are updating the memory. This cell state memory, you are trying to update it. So what is that you are planning to do it? So here now we will update the old state value, which is CT minus 1, into new state values CT. Okay, this becomes a new state after updation. Okay, updation, you apply the forget FT, then you apply CT minus 1, then you give the IT and CT bar. Okay, you are going to get it the CT. So forgetting the things, we decide to forget what we are interested in forgetting or forget earlier, then we add this. So this is what we are trying to do it. Okay, here firstly we multiply the old state, this old FT, that is FT into CT minus 1. Okay, plus this is concatenating or maybe like summation, element wise summing it. Then this IT, right? What is this IT? IT is the input. Okay, which new input, and whether it is need to be stored or not, deciding it. CT bar is the new thing that you are going to do it. You multiply this one again, element wise multiplication operation, and then you add it. This is IT into CT bar plus FT into CT minus 1. This is the output of CT that you are going to get it. Okay, this is what you are going to get it. So this one is scaled by how much we decide to update each state, right? Now the output gate, this is the fourth step that you perform in LSTM. Okay, so what do we do here? Basically we will run a sigmoid layer. Okay, maybe like we run a sigmoid layer which decides which part, okay, which part of the cell state we are going to output. Okay, which part of the cell state we are interested in output. So here if you see, it conditionally decides what to output from the memory. You see here OT. Okay, OT is, you see, this is the thing that you are supposed to do it. OT, this is the output. Okay, at time t is HT minus 1, definitely this HT minus 1 earlier value, then XT, the output of earlier value HT minus 1, and the current input you are taking and adding with a bias also. Okay, this is multiplied, the current input and the previous output is being multiplied with the output weights. Okay, the weights, some weights are added here, plus the bias. Okay, bias of the output, that is the third one. This is the output, and then you are trying to get this OT, this. Okay, passed through a sigmoid layer. Okay, passed through a, this is the OT value that you are going to get. Now ultimate HT, what you try to get it, this CT value. Okay, this CT value earlier what you have got from this memory update value, that CT value you passed through a, by passing through a tan H function, means giving a range from -1 to +1, multiplied by this output of this sigmoid layer. Okay, you are getting this HT. This is the output that you are going to get it. Okay, we are getting it. So we run with a sigmoid layer here. We run with a sigmoid layer which decides which part of the cell we are going to output. Then we put the cell state through the tanh, right? We are trying to pass through the tanh and multiply the output of the sigmoid gate, so that we only output the parts we decided to. Okay, so that we are this basically gives, or this output gate decides what to output from the memory. So this is all about the different states. One is the forget state here, forget gate, or the then the input gate. Then you have the memory status update at this third step. Then fourth step, what you are going to do have is the output gate deciding which output to be given. Conditionally decides what output to be given from the memory. So in summary, if you see it here, the whole set of functions, what takes place here, you can see these are the LSTMs. Okay, LSTM, different cells here. You give it here. So FT, you are going to compute it with what are the things, the previous input and the current the previous output from the earlier state and the current input from the current time interval. You are multiplying with some input, the forget weights, and you are adding some bias and then passing through a squashing function, and you are getting the FT. Then again, the output of the previous state at timestamp t minus 1, then again the current input. Okay, you are multiplying and with the input weight and with bias, input bias, then you are passing through a sigmoid layer, and then you are trying to get it the IT. Then this is the CT that you are trying to get it. Okay, CT bar. Okay, CT bar, you are trying to get it with the HT minus 1 and XT into HT minus 1 and XT into some weight added with some bias EC, and passing through a tanh function, you are going to get it the CT bar. This, then you are trying to do the updation of this memory status. Okay, memory status, memory cell updation, you are trying to do it. Like what you are trying to do, you are multiplying this both into multiplying this forget and CT minus 1, you are going to do it. Then output, what you are trying to do it at an output gate, you are this output, this HT minus 1 into HT multiplied with the output weight plus some bias, output bias, and passing through a sigmoid layer, you are going to get it the OT, output at time t. And then to regulate, what you are trying to do it, this OT, okay, this OT multiplied with this CT, the current state, okay, current CT value, current state value, uh, passed through a tanh function, you are multiplying it and you are going to get the HT value. So this is the complete state, you can say, about this LSTM. Complete steps, list of steps. These are the list of steps that are to be followed for a LSTM output. Okay. Now, so the LSTM training, you use again back propagation through time, which is most commonly used, and different weights. Of course, we need to adjust the weights with respect to different gates. Means like for the different gates, that is like the input gate, output gate, and forget gate used by this sigmoid layer. Okay, there also we need to change the weights. Also, input with respect to the tanh layer also we need to change it. Output depends on the task, what type of task that we are using it, whether it is a single output prediction for the whole sequence of steps or sequence of inputs, like as I say you that, like for a review, for example, you are trying to take the review. So sentence 1, sentence 2, sentence 3, like that, you take many words like that, sentences, and then ultimately you give it a review, sentiment analysis, like whether it is a true or false, or maybe like you state that like yes, I support it or I do not support it. Okay, true or false, giving like yes, you can buy or do not buy. So it means that you take so much input and then you give only one output. So this is a single output, like it is given the below here. So x0, x1, x2, x3, these are the different inputs passed through LSTM, and then you do the mean pulling, and then the output is taken using some logistic regression, you give the output, or one output at each time step. Maybe like for sequence labeling situations, like one output for each step, like language translation, for example, a language translation. Okay, I to I. Okay, or like that, simply direct translation means word to word translation. Suppose you are doing it generally in this one, many to many translation, it comes as many to many translation with some time period gap in language translation or machine translation. But suppose you are doing word to word translation, then the output differs there. Okay, what type of output that is required. So you can do various training activity like that. Then there are deep LSTMs. Okay, these deep long short term memories, like which you say that deep LSTMs can be created by stacking multiple LSTMs. You see here one LSTM stacked on another, stacked on other, like that. LSTM layers vertically with the output sequencing of one layer forming the input sequence for the next layer. Okay, in addition to the recurrent connections within the same layer. And uh, for this you can this basically this deep LSTMs increases the number of parameters, definitely, but given sufficient data it can perform highly better than the single layer LSTMs. Of course, there can be some dropouts which are usually applied only on the non-recurrent edges between. So wherever you can have dropouts, means you can completely cut out that values uh, for non-recurrent edges only. Okay, so like for example the outputs like one to many to one. So maybe like in every layer or every step you need not give the output, so that can be a dropout. Okay, or maybe like once you give the input, then afterwards you need not give the input, but after some time period you try to generate the outputs. Okay, uh, you also have bidirectional RNNs which are more powerful nowadays. Okay, so data can be processed in both directions, processed with the two separate hidden layers, which are then fed forward into the same output layer. You see here the bidirectional RNNs can better exploit context in both directions. Maybe like given a word, okay, from forward and backward, it can try to get the context. For this is for the best results, to attain the best results. For example, bidirectional LSTMs perform better than unidirectional ones in speech recognition. So for the purpose of speech recognition, maybe like what is the best word. Okay, you take see like earlier for word embedding, what we have seen, you take the context and you try to predict the what is the best word, right? What is the best word for this particular context. Or maybe like from taking the word in skipgram, you are trying to predict what is the context. So in this way also, from backward, so suppose I am trying to predict what is the next word. Okay, what is the next word, then in that case what it can happen is like I try a set of sentences, and at forward I see that what is the best word, and from backward, given this word, maybe like are these the best context words, I can find out. So combining both the results, we can give output, like if it is the best one, best word, or any other word that is again available. So trying to give the best word, that is, so we can use this bidirectional RNNs also can be used. So this is what we have seen today, LSTMs and various versions of LSTMs. CNN LSTMs are also available like that. Okay, uh, we can use that things also are available, but this is restricted with respect to this particular class. The concept is restricted here up to this class only. Okay, or up to these concepts only. So any other doubts, you can please ask me now.